Welcome everyone. First of all, if you did not qualify for the SMO Round 2, do not close this video immediately and say this is of no relevance to me. For today's video, even though it is preparing Round 2, I would suggest that you would like to prepare for next year's Round 2. Preparing for Round 2 is something that takes quite a long time, and it's also something that is not easy to do. So in this video, I just want to talk a bit about how does the preparation actually look like, and specifically, how do I use the solution book? Now, many of you have a copy of a SMO solution book from whichever years that you have purchased, or you have gotten from your school, or you have found online, or you have borrowed from the library. For round 1, it is okay, usually. For round 2, not so much. For round 2, we have a very obvious problem of where did that come from? What is this saying? I do not understand this, please help. Before we go through a few example questions to help you understand how round 2 solutions should be read and understood, I would like to first just emphasize what it is and what it is not. Now, the round 2 solutions, they are minimal solutions. They are not readable solutions. Now, what I mean by minimal solutions is that if you were to submit the solution that was in the SMO solution book, you would get 10 marks. A readable solution is something that I can understand. The solutions in the solution book are not readable solutions, they are minimal solutions. So they are also not teaching materials. In other words, they are also not good for learning. Well, not in the traditional sense anyway. When you're writing the SMO solution book, just like most Olympiads, the solutions are written in a way that justifies that the question setter was not wrong. It is not meant to help you understand. Now, the same thing should apply for your solution writing. Your solutions can be minimal, but I would still suggest that you try to make them readable, because if you made them readable and there was some small error, you'll be probably fine. If you made them just minimal, which means very few details, and you were wrong, you probably don't get very many marks, because the person reading it truly has no idea what you're doing. So I'm going to show you 3 examples, and the examples are taken from the SMO Senior. The 3 examples are taken from the SMO Senior of 2008, 2009, and 2010. Just for convenience, I've taken the last question, which is also, in theory, the hardest one. Now, I've included the official solution below because we're going to talk a bit about how do we actually learn from that solution. And sometimes we're not going to learn very much from the solution below, but we can use that as sort of a reference. Okay, so this question from 2008, they're all from Senior. So for those of you in Junior, maybe it may be a little bit newer to you, but I think you can still understand it. Now, the idea here for this is that we're just given an inequality to prove. We're given an inequality to prove, and when we're given an inequality, before we look at the official solution, I would just like to comment on the fact that you would like to try to find the equality case anyway. You will try to find the equality case, and the equality case here meaning when both sides are equal, appears to be when everything is 1. Now, are there other equality cases? At this point, I have no idea. Now, another thing I would like to comment is just that for all of these questions, you really would like to try them before reading the solution. But in the course of this video, I'm not going to go through the process of trying the question. I've already tried the questions beforehand. If you'd like to pause the video and try the question first, please feel free to do so. Now, the official solution starts off with, for any real number t, we have 2 times 1 plus t squared cubed equals to 1 plus t cubed times 1 plus t whole thing cubed plus 1 minus t cubed times 1 minus t whole thing cubed, which is greater than or equals to 1 plus t cubed times 1 plus t whole thing cubed with equality if and only if t equals to 1. In particular, for non-negative t, 2 to the 1/3 1 plus t squared over 1 plus t is greater than or equals to 1 plus t cubed to the 1/3 with equality if and only if t equals to 1. Did anyone get that? I most certainly did not get that. So the first thing to understand is that the official solution is usually going to be written after solving the problem, not before solving the problem. Before solving the problem, when you read it, it makes no sense. The second thing that you want to realize is that usually, to a large extent, the solutions are written in a reverse direction from how you actually figured it out. So if you like to read the solution, you should try to look at it in reverse order if you haven't solved it yet and you're trying to understand where the solution came from. Now, in an inequality question, each of the greater than or equal to operations represents kind of a step. So I want to first look at this, and to understand it, just go through the steps and find where they came from. Now, the first step came from this thing here, which I still don't understand. So I'll deal with that later, but that's the first step. This is just expansion to get to the second line. Now, where did the third line come from? So I need to do a bit of spot the difference. How do these two actually differ? And I see that this is the same, this is the same, this is the same, and okay, so what happened is that this is actually AMGM applied on two separate portions. So AMGM was used on a cubed plus b cubed plus c cubed is greater than or equals to 3abc, and likewise for the three terms in the blue boxes. So this is AMGM twice. Okay, now the next thing to figure out is what's the final line? And when I look at this, I realize that the final line here, this is actually not really an inequality. This thing here is actually just 1 plus abc cubed to the 1/3, which is equal to 1 plus abc. So this thing here is actually, this is important to understand, it is not mathematically wrong to say greater than or equal to, but in terms of understanding, it is not very good. Now this is also true when you write your solutions down, right? So for example, if you were doing modulo arithmetic and you said something like, for instance, x squared minus 2 is congruent to x squared minus 9 mod 7, which is then congruent to x plus 3x minus 3 mod 7. Now the first congruent is congruent mod 7, but the second congruent is actually just equal to, right? X squared minus 9 is equal to x plus 3 times x minus 3. Now when you're writing down your solution, if you just wrote it as congruent mod 7, you're not wrong. But if you're trying to understand what's going on, you want to realize that, oh, that's not modular arithmetic, that's a factorization. So the same thing applies here. You want to understand that this is not actually an inequality. So really, there are only two steps that were done. The two steps of inequalities were, one was AMGM and the other was this weird thing that is in star. Okay, now let me continue to try to tear this thing apart. The skeleton of the solution is basically left hand side is greater than or equal to this product, and then it kind of just shoots straight to the right hand side already. Right? The algebraic simplifications, I consider them to be relatively non-inequality steps. So if we are here, we know how to simplify them. The main thing is, where did this come from? Why would I think of doing this, and where did it come from? Now, here is the idea that would motivate this, and it's not mentioned. Now, the motivation, which is also a simpler proof of this statement here, is Holder's inequality. Now, Holder's inequality is a generalization of Cauchy-Schwarz. So Cauchy-Schwarz is, you have got a product of square roots is greater than or equals to the sum of geometric means of the respective terms. Now this is with cube roots and 3 sets of terms. If you're not familiar with Holder's inequality, well, it would be hard to figure this out. But what Holder's inequality would actually do is that, just like your normal Cauchy-Schwarz, you take the geometric mean of all the first terms, and you take the geometric mean of all the second terms, which would be now ABC, and that is essentially what Holder's inequality does immediately. So this entire portion here is just one application of Holder's, despite how it has been shown here, which is expand, use AMGM, and then notice that this is a cube. But still, this doesn't fully explain how did you get this. So we have now to ask the question, all right, why would you think of doing something like this, even if you did know Holder's? Now the answer to that question is that when I look at the problem, I kind of want to slice it up. I realize that there are sort of 3 identical functions applied to A, B, and C. So the function being fx equals to 1 plus x squared over 1 plus x. Now the fact that it appears 3 times means that you just want to deal with it once, and so the idea therefore that would make sense is that I want to show this so that the left hand side, which is FA, FB, FC, is going to be bigger than GA, GB, GC for some other function G, and I would like this other function G to be such that I can compare it to the right hand side. And conveniently enough, because if you know Holder's, you know that the only thing that can obviously be compared to 1 plus ABC from 3 separate functions in terms of A, B, and C is Holder's. It would make perfect sense to try to say that your right hand side is less than or equals to 1/2 of this product, that we have below. If we have this, it would then cause us to try to see if it is true that 1 plus a squared over 1 plus a is going to be bigger than this, with a little bit of the extra constants just being a nuisance. Okay, so once I have this, I am left with the task of checking whether 1 plus x squared over 1 plus x, this is the function here, is greater than or equals to the cube root of 1 plus x cubed, with kind of an extra 1 over cube root 2 being dispersed to each of these three, which you could write in this form. So this would be what you actually would want to verify. You would cube both sides. And quite frankly, this is just unnecessarily clever looking. You can just expand both of these entirely and see what you get. So 2 times of 1 plus x squared cubed greater than or equals to 1 plus x cubed and 1 plus x cubed. You see that this is the statement here now. This is what we have arrived at reasonably, although probably as the last step and not as the first step. So down with this word first, right? This is a horrible way of presenting it from a learning perspective. If I want to show this, don't follow this, because you must understand that this is a very simple single variable inequality which you can just expand out and compare. Now, as solution writers, we are a little bit lazy sometimes, and so we just do not feel like writing that much. I am very guilty of this at times, but that does not mean it is the best way to understand things. So you can compare this, subtract off this from the other term, and hopefully it should be factorizable. Now, I am writing all over the place in one humongous mess. This is going to happen, and you have to be willing to write all over the place in one humongous mess when doing your solutions as well. Do not start writing the so-called final solution when you are starting the problem. No, write a big mess and then treat this as a draft. Once you've figured out, then write the solution properly. If you try to write it out in complete sentences immediately, you are going to waste a lot of time. So anyway, in this particular statement here, how am I going to show that that is always positive? Well, I can see that there is a factor of x minus 1 since equality was at x equals to 1. Remember that at the start we mentioned the equality case. So we know that would allow us to show this to be true, and of course I would prefer to do it in a slightly more neat fashion, so I would group them in this way. And then you can actually factor out x cubed minus 1. And this will be x minus 1 x cubed minus 1. I believe that you would end up with something that looks like this, which is x squared plus x plus 1 times x minus 1 to the power of 4. And this is clearly greater than or equals to 0. Do you understand what I mean if I were to say now that we need to solve the solution? So the solution is not really going to be incorrect in any aspect if you go through it line by line. But going through it line by line is practically useless because this question is not going to show up again. Well, not exactly. Most likely. This is what you should be doing, and let's look at another example of a different problem type. This was an inequality. Let's now look at a combinatorics problem. Now this is a fairly short solution. Please note, short doesn't mean good. So it doesn't mean that a short solution is superior. It is shorter to write, but that doesn't make it easier to understand. Short also does not mean easy. There have been many solutions that are very short but very hard to think of. So do not look at it and say, hey, this question is quite easy. The solution is only like 1 paragraph long. Let's look at the question. In an archery competition, there are 30 contestants. The target is divided in 2 zones. A hit at zone 1 is awarded 10 points. A hit at zone 2 is awarded 5 points. No points awarded for a miss. Okay, so zone 1 is 10 points and zone 2 is 5 points. If you miss it entirely, you get nothing. Not surprisingly, each contestant shoots 16 arrows at the end of the competition. Statistics show that more than 50% of arrows hit zone 2. Okay, so numbers, I can count it straight away. There are 480 arrows. So not greater than or equals to. Greater than 240 hit zone 2. The number of arrows that hit zone 1 and miss the target are equal. Prove that there are 2 contestants with the same score. Now the solution is unreadable. It's unreadable because it just starts with contestant I hits zone 1, AI times zone 2, BI times and miss the target, CI times then the total score. Like, why am I calculating the total score? And why do I care about positive and negative numbers? And why am I this is all very weird. So this is a case where the solution is practically pointless apart from a few keywords, which is that there's a pigeonhole principle. I should think of it as being like, okay, so positive or negative is somewhat important, and scores are all distinct is basically supposed by contradiction. Now, the word contradiction never showed up in the solution here, but it is approved by contradiction nonetheless. I pretty much want to just ignore this for the time being and just try to do this in my own way first, and from time to time I'm going to look back at this solution and see whether it makes sense. You want to get the feel for a question when it is this kind of statement, at least for why it may make sense. That's a very weak condition, right? Because for round 2 questions, for any proof, we're trying to say why must it be true. I am only asking you to start by thinking of why it may make sense. There's a long way between that, because why it does make sense is not even a proof. But I'm even asking why does it possibly make sense. But that's the level of intuition that we all start from before we construct a proof. Prove that there are 2 contestants with the same score. Now, first of all, I can look at why this may make sense because there may not be many possible scores. So let's literally list out the possible scores. Now the possible scores are all multiples of 5 because there are 10, 5, and 0 for zone 1, zone 2, and a miss. So the possible scores are going to be 0 to 160 if you hit zone 1 every time. In total, there are 33 possible scores. But there are only 30 contestants, so even though it now makes a bit of sense that, well, there is quite a high likelihood of 2 contestants being at the same score if this were a real competition, I can now maybe go one step further. So there are not many possibilities is why it may make sense. But this is not any competition. This is a competition where I am told about this. Now, more than half hit zone 2. This is pretty much saying that there is low variance. It's sort of like how the SMO Round 2 is like. For most questions that are very easy, almost everyone would solve it. For most questions that are hard, almost no one will solve it. So there's very little actual variance in scores. There's very little variance in score here. And therefore, it makes sense that they are clustered. So that is a bit more support for them getting the same score. They're clustered near the average. Now, the other thing that it mentions to me is that the number of arrows that hit zone 1 and miss the target are equal. And I'm not quite sure what is the significance of that yet. But I'm now going to try to improve my intuition further. So I've gotten to the point of, this is why it makes sense. Now, a step further of like, but how do you know that it must happen? Let's try to create a counterexample. In other words, if you still don't feel very convinced, try to show the question is wrong. Now, in 2011, where I took the SMO Senior, I didn't include that. 2011, there was indeed a question where it was wrong. Most of the time, that's not true. But this is the correct philosophy to take if you can't figure out why. Like, try to break the question and figure out why it doesn't break. So an attempted counterexample. I want them to all have different scores. They are clustered near the average. So imagine that I have a person who scored 80. And then after that, now I say, okay, I'll have one person that scored 175 and 185. And then another one who scored 90 and 70. So I'm trying to spread them out, but not spread them out too much because I say they're clustered near the average anyway. Now, if I were to try to cluster them this way, it means that that's good because I have more of the zone 2 arrows, so it should not be too far away from AT. So I'm going to try to have the counter example, but as I'm trying to counter example, I would notice that there are, well, an odd number. So maybe if I don't want to include 80, let's try not having 80, and I'll just have, out of these 30 contestants, 15 go up and 15 go down. Now, if I did that, 15 go up and 15 go down, you would be left with this sequence of scores. Now that would be also consistent with the zone 1 and the misses are equal. Now I want to know why this is wrong, and so apparently the only thing that could possibly be wrong is this, because everything else is satisfied. Zone 1 and misses are equal just means the average is actually 80. So I only have to figure out, well, this person here with 85 needed at least one arrow in zone 1 to get away from the average, which is 80. And in fact, every time when you want to get one step further away from the average, you need one more good arrow, or for the bottom half, one more bad arrow. So this is how many good arrows you need. And the sum of these is 120 zone 1. That's the problem, isn't it? The problem is that I can't get far enough away. I can't get far enough away because if there's more than 240 hitting zone 2, that means that there are less than 120 in zone 1. And less than 120 that means they're the same thing. That's basically the solution, isn't it? The solution is that if I try to get away from the center, even if I just do the minimum amount of getting away from the center, I already am in trouble. And this is then how the solution is going to look. If you now look at the first sentence, this is just simple multiplication. If you look at the second sentence, it's saying that, well, each zone 1 gives you a +5 compared to average. And each miss is -5 versus the average. That's basically what this second sentence says. Now, the suppose by contradiction is the same thing as we have done here. By the pigeonhole principle, half of these are either positive or negative. Now, we did this here because we wanted it to be symmetric. If let's say that I put in one of them to be 80, I can at most chop off something from one of these. There will still be one of the directions where there are 15 that are above average or 15 below average. So the numbers AI minus CI must all be distinct. This is just saying that the positive AI minus CI is just above average, and the negative AI minus CI is below average. So there will at least be half of them above average or below average. And so in the positive case, which is if there are 15 of them above average, then the number of, so the AI minus CI is this. What I've written there, which is how many arrows in a good arrow sense, or for the bottom half, a bad arrow sense, do you need to escape the average? And this is what we are told. AI minus CI is greater than or equals to I, because yeah, I mean 1, 2, 3 to 15. You have 15 different numbers, they will at least be 1, 2, 3 until 15. And therefore AI is greater than or equals to I. That's what we said by common sense. And so this was the thing we calculated just now, and then there is a contradiction. So the solution actually is not saying anything very fancy, but by writing in all this notation, it artificially looks bad. Now, AI minus CI is greater than or equals to I. It's not actually correct because this is also a without long. Now you see that in this question, in this solution, it is technically not completely correct, because without loss of generality, let this be greater than 0. Why can't it be that A1 minus C1 is going to be 15 and A2 minus C2 be 1? So this is technically not correct. There is sort of one extra thing, which is that you should assume this as well, which they did not write there. Now, this will also give you a bit of consolation. When I said minimal solution, if you forgot to say some things like this, you're not going to get marks deducted unless it's a serious logical error. If it's just, well, I can tell what it is trying to say in retrospect, that's good enough. And remember that the person reading your solution also already knows the solution to the question. So that's one good thing. When you're reading the solution and being very mystified, remember that you do not know the solution. When someone is reading your solution, they know the solution. At least they know a solution. So that gives them a better chance of understanding what you are saying. Let's look at one final example. And if you are looking at how long this video is, this is why round 2 is not something you can prepare for in a couple of weeks, especially for something like senior or open. Many of you have asked, how do I prepare for SMO senior? And that's the name of this video. Sorry, SMO round 2. The answer to that question is, if you want to prepare for next year's SMO, or if you already have done plenty of preparation and you are now just in the closing stages, this is what you can do. Squeeze out every drop out of every single question. Don't read the solutions and say I can understand them step by step, because this is horrible. If you were trying to understand this step by step, nightmare. So if I look at a solution like this, I'm going to straight away say, you know what? Forget about it. I do not understand this solution. But I could understand this solution. It's just a bunch of algebraic steps. So I'm going to read the question, read the solution back and forth if I'm trying to understand what's going on. And I am going to sort of translate this into simpler terms. Okay, so let p be a prime number. Let a1 to ak be distinct integers chosen from 1 to p minus 1. And for 1 less than or equals to I less than or equals to k, let ri n in brackets here denote the remainder of the integer nai under division by p. Okay, so what exactly is this notation? Essentially, this rin is just nai mod p. In the programming sense of mod p would automatically be between 0 and p minus 1. In the math sense, of course, mod p is just an equivalent. So I could say that 1 is congruent to p plus 1 mod p as well. But for the rest of this question, it is okay if I designate the mod p to mean the simplest form mod p. Now, S is the set of n's such that r1n less than until basically just in order. So the ri to the n's are in order, and show that S has less than 2p over k plus 1 elements. Now, this is the kind of question where you 100% would like to make sure you try a small case to just understand what's going on. So let's try something like p equals to 5, and let's try something like k equals to 3. So I will just pick from 1 to 4, so I will do it in a random order. So maybe this is 2, this is 4, and this is 1. Now I want the n's such that these are in order. So if n equals to 1, R1, 1, R2, 1, R3, 1 are just 2, 4, and 1. This is not in order. For n equals to 2, it means you multiply all of these by 2. This is still not in order. If I multiply them by 3, this is in order. If I multiply this by 4, this is not in order, and so I just got 1. Now, 2p over k plus 1 in this case is 2.5, and so I wanted there to be at most 2.5, which sure, I only got 1 here. So this is what is going on in the question. What's going on in the question is effectively pick a bunch of numbers, take all their multiples, and how many of these sequences are going to be in order. I claim it is at most this many. Now you notice that there is very little actual restrictions on sequences of stuff down here. And so, for example, A1, A2, A3 could have been in any order I want. They're not in ascending order to begin with. So this is interesting. Now another thing that is interesting is just about the fact that it says 2p over k plus 1. So it means that I am just asserting that my chances of success are pretty low of getting them in ascending order. Now this makes perfect sense to me actually. If I have got, for example, k equals to 2 and my 2p over k plus 1 becomes 2p over 3. So it is saying that less than 2/3 of the time am I able to make it such that the smaller one versus the bigger one is in the correct order. That's not very surprising at all. So this makes perfect sense. That it should be quite rare that when you just take a multiple of everything and then you want to check whether they're in order, it should not happen most of the time. Now, extreme case would be sort of like if you did something very small, like k equals to 2, a1 equals to 1, a2 equals to 2, and let's say p equals to like a big prime number like 101. Now, if you did this, then n equals to 1 all the way to n equals to 50 would work. And then when you went to 51, it would overflow and it would no longer be true after that. So it would give you about half. Now, as I said, for this video, I'm not going to try to solve the whole question. I just want us to understand. So when you read the solution, you say, I don't understand the solution. At least try some small case to be able to get used to the notation first. Now let's look at the questions here. Sorry, the solution here. It says let r naught n equal to 0 and rk plus 1 n equals to p. Do those mean anything in the question? Not really. So they are, I don't know what that's for yet. So let's ignore that and read what this thing is. S prime is the n such that for the sum down here, you get p. Now that kind of makes sense. If I am reading it, this is the sum of differences being exactly equal to p. And it starts off with r1 minus r0. I'm going to ignore the n on top first, just for brevity. So it's the bunch of successive differences. Now if I use my example, which is that with the p equals to 5 and k equals to 3, it just means that put a 0 in front and a 5 behind. The difference would be 2, 2, 3, and 4. That does not sum to 5. This would be 4, 1, 1, and 3. That does not sum to 5, but this will be 1, 1, 1, and 2. That does sum to 5. So it's just saying that if you go in ascending order, then it will go just forwards from 0 to p. If it goes backwards at any point, you will end up on your number line. You are just going to sort of be doing some forward, backward movements, which will end up giving a distance that is more than p. So this is what is going on here, and that's actually what the next statement says. The next statement says that, yeah, this is the condition that you have. So therefore, the size of S equals the size of S prime. This is just telling you that S prime, this is an equivalent condition. In fact, this is not just the size of S equals to the size of S prime. It's just the sets are the same. So once again, by saying the sizes are the same, it's a bit misleading. It's true but misleading. It's just that these are the same sets. Continue reading. Since for n in S prime, this is equal to this equals to this. Yes, so we know that for each of these, if they are in ascending order, which is basically for those that if n works, is what this means. If n works, all of these remainders are in ascending order. So if they are in ascending order, then what is this difference? This difference is just going to be, by definition, n times ai plus 1 minus n times ai. Where p doesn't divide this here. And so, therefore, if we are looking at our number line, it's saying that these are all just going to be different sizes of jumps. Now you will also realize that that is said in a rather weird sense. We are basically, what this thing is just saying is that if they're all distinct, if I took n times x1, n times x2 until n times xk, where this is the x are the differences, if the x1 to xk are all different, then these should be all different. Right? Because p does not divide ai plus 1 minus ai. It's just if I call this thing xi, or maybe I should call it d for difference. Now, even as I say that, I realize I've confused myself. Now, this does happen, right? When you read the solution over and over again, you get more and more confused. So let's just repeat that one more time. Now, this does happen where you can take 10 minutes to understand a single line. Don't feel bad to take 10 minutes to understand a single line. If you're asking yourself, how would I have thought of this? Well, just like the inequality just now, we understand the solution first in terms of what it says, and then we will understand why it makes sense a bit later. So if n works, all of these differences, which the absolute difference is just their normal difference, this is by definition, because ri plus 1 to the n and n is just n ai plus 1 and n ai mod p. So this is by definition. Now, p doesn't divide ai plus 1 minus ai. That's also by definition, because these are distinct and from 0 to p minus 1 based on the question. Sorry, from 1 to p minus 1. Because of that, it means that these numbers are all distinct. Where n is varying. So I realized that I have misunderstood it just now. This is distinct for the n varying. Now, it's not for all I. So I misread this. This is not I. This is n. In other words, it's saying that ai plus 1 minus ai times different things. Times 1, times 2, all the way to times p minus 1. Now, it's important to read the notation very carefully. So this means as n varies from 1 to p minus 1, not as I varies. Now, they both could vary. So now I understand what's going on. I understand that it is actually, these are distinct. Now, that makes sense, because the difference between these would be a multiple of ai plus 1 minus ai, which is not a multiple of p. Okay, so what am I actually doing? I'm looking at the n's which work. So for the n's which work, for example, in the k equals to 2 case, it just means that this difference is 1, this difference is 2, this difference is 50. All of these differences are different. That's what it's saying. For the ends that don't work, like for example, here we saw some repeats. Although when I said the repeats here, this is one that works and this is one that doesn't work. So that's okay. For the ones that do work, there is going to be no repeat between the different values of n. Okay, I get that. And so therefore, now what is this? Therefore, anyone can read this? Okay, so let's just slowly understand what is going on once again. I want to know what does this have to do with everything else. The first thing I see is that this is P. And this is summing over all the ends that work. Okay, so what's happening here? Now what is happening here is simply that I am actually trying to count in two ways. You notice that here there is a reverse in the order, and so therefore again this should be equal. This is not greater than or equal to. That is deceiving. It's just equal to. I just swap the order of summations, which means that for those of you who do some programming, right, if let's say you're looping over I and j, you can loop over I first or you can loop over j first, and it doesn't matter as long as you're covering the same set of things. This double summation is just for all ends that work, and then after that sum all the differences for those n. And you just can write it in two different ways. Now the first way would be just that there are this many sets of P. Of things summing to P. And the things are just the thing in the blue highlighting, which I'm a bit lazy to write out again. Now when I reverse the order, it means that I'm looking at, okay, so the first end that works, I've got this bunch of things. The second end that works, I've got this bunch of things. The third end that works, I've got this bunch of things. All of them sum to P. And then I've got this S prime, many of them. Instead of summing it row by row, I sum column by column. I sum column by column, and I said already that they are distinct. Now because I said they are distinct, it means that there are going to be these many things which are distinct. And so their sum is at least going to be 1 up to this size of S prime. The number of things here is just, well, the number of columns here, even though I only showed 3 columns, there aren't 3 columns, the number of columns is 0 to k. There are k plus 1 columns. The k plus 1 columns is the differences in here. These are these. And so therefore, what I am trying to say is that I cannot have too many things in my S prime. I cannot have too many rows, because the number of rows will affect the sum of each column, and I already know the number of columns. And so the sum here is what you got down here. And therefore, the size of S, which is the same as the size of S prime, is going to be limited by that. Why? Because of this. So in other words, we were always trying to say that you cannot have too many rows, because if we have many rows, then the sum of each column is going to be quadratically big, whereas the number of rows themselves is only going to be linearly big. So that limits how big the size of your table / matrix here can be, i.e. the number of things in your S prime. Now this is a hard question, but you must go through it, trace it bit by bit, really understand it, and if possible, get a picture. So the picture is that this is summing in two ways. Now this summing in two ways, this swapping summation order, again, is a relatively famous thing that we do, which is known as Fubini's principle. Fubini's principle, if you just Google it, you're going to find some weird stuff about integrals and infinite sums, because that's for undergrad level math. Now at this stage, it's just counting in two ways. And counting in two ways is a very reasonable way to try to bound something, and that is the reason why the question in the first place gave you the condition of things being sorted in order, but we chose to translate sorted in order to something that is of this sort. Sorted in order means that the jumps are all in the same direction. So like 4 to 3, the difference of 1 versus 1 to 2, the difference of 1 are in different directions. Whereas you want them all to be in the same direction so that you can compare them to each other directly rather than indirectly. This is the final thing, right? You can see this video is an hour long. The SMO Round 2 is hard to prepare for, but it requires the effort. For everyone that asks me, how can I prepare? I have 2 weeks left. I can just tell you, you cannot prepare from scratch. If you have never done round 2 before, your best shot is just to try to do one question. Be it junior, senior, open, hope to solve one question if you have never done the SMO Round 2 before. If you have done some before, obviously your objectives will change a bit, but this would be how you would go through the questions one by one, whether it be SMO problems or if you're going to try questions from other countries as well. Read the solutions, really digest it very carefully. It's better to spend 1 hour productively on 3 questions than spend half an hour on 3 questions and get nothing out of it whatsoever. I hope this also helps you to understand why it takes so long. With the solution, I spent 1 hour talking about 3 questions for you to figure it out, and then to write out the solution yourself could easily take 1 hour for 1 question. Why is the SMO Senior and Open 4 hours for 5 questions? I think you can quite easily see why that's the case. Okay, so thank you for watching this fairly long video. Feel free to share any comments on these questions, and for the experienced competitors among you, also feel free to just share your experiences in the SMO Round 2 so that it will be of help to those of our friends who are a little bit newer to the SMO Round 2. It's not a competition where you're trying to just protect the knowledge that you have. If you have done Round 2 before, you are already at a huge advantage, so you do not need to feel afraid to share a little bit with some friends as well. Thanks again, all the best, and I'll see you again when we review the actual SMO Round 2.